So next we'll try to understand the postulate of equal a priori probability. Okay, so before that we should know what do you mean by probability. So basically the probability corresponds to random events or random selections. Okay, so probability is defined for random events and random selections. So basically probability is possibility of that event divided by total number of events possible. Okay, so that is how you can define the probability. Okay, so for example, the tossed fair coin falls either facing head or tail up. Okay, if you toss a coin, there are only two possibilities. Either it can face head or it can face tail. This event is random and perfect prediction is impossible. Okay, this particular event is random and the 100% prediction is impossible because there is a equal possibility, either head or tail, that can be shown by a particular the unbiased coin. The possible number of events are two in a number. Only two possibilities are there. It can show head up or it can show tail up and are equally likely to occur. Okay, there is no biasing. So they are having the equal probability. Therefore, these two events have the probability of 1/2 or 50% probability. Okay, so basically this 1/2 is obtained by taking the particular possibility divided by the possible event divided by total number of different events possible. What are the total number of different events possible? Two events are possible. Either the coin can show head or tail. Two events are possible in which the considered event is, let us take head up. Head ತೋರಿಸ್ತದೆ ಅಂತ ನೀವು consider ಮಾಡಿದ್ರೆ, then definitely that is one event. That is one event divided by total number of events possible. That is giving you the probability of that particular event. So 1/2 is the probability of observing the head if a coin is tossed. Okay. Similarly, the probability of showing tail is also half. So total probability of all the events, that should give you 1. Okay. So that is giving you the conservation of probability. Okay. So just remember, in this particular case, the probability is going to be half. Okay. To observe the head when coin is tossed, that is probability is half. So probability of showing tail is again half. And these two events are equally likely to occur. Okay, they can occur with equal probability. So both are having the half probability, and that is how the microstates or the observation of the events are going to be equally probable, and that is called as postulate of equal a priori probability. Okay, equal a priori probability. Just I will try to give the mathematical relation for probability. The probability of an event is defined as the ratio of number of occurrence of events to the total number of events happened, provided the number of events are very large in number. Okay, the probability of event is defined as ratio of number of occurrence of events to the total number of events that happened. Okay, so provided the number of events are very large in number. Okay, so let us take the example of that tossing coin only. Suppose we toss a coin, the observation of head, let us take 500 times I will toss the coin. In that case, you may observe the head with 250 or 255 times out of 500 times. Okay, so that is the probability of observation of head is 255 by 500. It is nearly equal to half. If you take very large number of such events, definitely it will reach, or that will converge to half, 50% probability. Okay, so mathematically, the probability of certain event can be expressed as P is equal to n divided by n, where small n is the number of certain events divided by capital N is the total number of events that has observed. Okay, so that is giving you the probability of the particular event. Okay, simple example is tossing of coin. Similarly, you can take the example of dice. If you take one die, okay, if you toss the die, it may show one number out of 6 possibilities. What is the probability of observation of the number 6 by tossing a die? So definitely that is 1 divided by 6, because there are 6 different possibilities are there. Out of 6 possibilities, we are observing only one possibility, that is observing the number 6. So definitely 1 by 6 is probability of occurrence of the number 6. Similarly, the probability of observing number 5 is 1 by 6. So all events are equally probable. Okay, and that's why in the ensemble, the large number of elements are distributed in different possible microscopic states characterized by the same macroscopic variables N, V, and E. That is what's already discussed in the previous class. So basically, the ensembles have different microscopic states with the same macroscopic variables or same macroscopic properties. According to the theorem, the fundamental postulate of statistical mechanics is that macroscopic system in equilibrium is equally likely to be in any of its microscopic states satisfying the macroscopic conditions of the system. It is called the postulate of equal a priori probability. Okay, so that means there is no preference for any event. So every event is preferred equally. Okay, equal a priori. Okay, equal a priori means every event is preferred equally. So there is a equal probability. Okay, under ಪ್ರತಿಯೊಂದು event ಕೂಡ unbiased ಆಗಿರ್ತದೆ. So priori term ಏನು ಹೇಳ್ತದಲ್ಲ, it is equally preferred. Okay, so basically postulate of equal probability ಅಂತಾನು ಹೇಳ್ತಾರೆ, otherwise postulate of equal a priori probability ಅಂತಾನು ಹೇಳ್ತಾರೆ. Okay, so priori means each and every event is having the equal preference of occurrence. Okay, so remember you can find different microscopic states for the given macroscopic properties. Remember, all the ensembles have same macroscopic properties, but they will have different microscopic states. Okay, they will have different microscopic states. So just you remember this particular concept. Okay, next, so this is the fundamental postulate in statistical mechanics that says that a macroscopic system in equilibrium is equally likely to be in any of its microscopic states satisfying the macroscopic conditions of the system. So this is called the postulate of equal probability. Okay, this is called postulate of equal probability, or it is also called as postulate of equal a priori probability. Okay, so next we'll understand what do you mean by thermodynamic equilibrium and what do you mean by thermodynamic probability. So thermodynamic equilibrium andre ಏನು ಅಂತ ನೋಡೋಣ. According to the postulate of equal a priori probability, all microstates are equally probable. So if you take the example of tossing the coin, head and tail are the microstates. Okay, macrostate is the coin is tossed. Okay, so you will not have the complete information of the end process. Event ಬಗ್ಗೆ ಪೂರ್ತಿ complete information ಸಿಗಲಿಲ್ಲ, that is macrostate. Microstate is giving you the particular number of events, head or tail. Okay, over a long period of time, every microstate would occur as often as the other. So there is no biasing. So all microstates are equally probable. That's why head and tail, if you do the tossing of coin number of times, very large number of times, both head and tail are observed to be equally probable. Okay, so ಎಷ್ಟು ಸಲ ಹೆಡ್ ಬೀಳ್ತದೆ ಅಷ್ಟೇ ಸಲ almost equal number of times you will get the tail. Okay, if you do very large number of experiments, very large number of events, definitely all microstates or every microstate will have equal probability. Also, in the development of ensemble, it is considered that the average values of macroscopic properties of the system in the ensemble should be time independent. So remember, macroscopic properties are time independent, but we have to take the microscopic states as a time dependent. That is very important. So macroscopic property means pressure, temperature, volume. They are time independent in a short interval of time, macroscopic property of the system. But microscopic states are going to be time dependent. They will vary with time. So according to these 2 points, properties of an ensemble are independent of time, and therefore the ensemble is said to be in thermodynamic equilibrium. Okay, andre now statistical mechanics in yaವಾಗ apply ಮಾಡಬಹುದು? If you want to study the system in thermodynamic equilibrium, then also the microscopic states are going to be changed, but the macroscopic properties or macroscopic states are going to be same for all the elements of the ensemble. So that is called as thermodynamic equilibrium. Thermodynamic equilibrium means the properties of ensemble are independent of time. Okay, then also you can observe the variation in the microstates. Okay, note the difference here. If you study the classical thermodynamics, so you will not observe the microscopic states, only you will study the variation of pressure, variation of volume, and variation of temperature and entropy, and with that you will relate one coordinate with the other. But here you can study the system even in the thermodynamic equilibrium by considering the variation in microstates. That is the main difference between the statistical mechanics and classical thermodynamics. Classical thermodynamics now microscopic states and study ಮಾಡೋದಿಲ್ಲ. Interaction between the molecules, interaction between the particles of the system will not consider mainly. Okay, andre ಅದನ್ನು ಕನ್ಸಿಡರ್ ಮಾಡ್ತೇವೆ, but major consideration is given only to the thermodynamic coordinates, pressure, volume, temperature, and entropy. But if the system is in thermal equilibrium, those coordinates are not going to change, but internally the system is going to have different microstates. So that is how the statistical mechanics takes care of the microscopic states of the system. Next, what do you mean by thermodynamic probability? You will see, for an ensemble corresponding to every macrostate, there would be a large number of possible microstates. Okay, for every macrostate there will be large number of possible microstates. Among the microstates, the number of possible microstates corresponding to given macrostate is known as thermodynamic probability of the macrostate. This is usually symbolized by omega. So omega is given by Ni divided by N. Okay, so that is where Ni is the number of microstates for ith macrostate, and N is the total number of possible microstates. Total ಎಷ್ಟು microstates ಇದೆ ಅಂತ ನೋಡಬೇಕು. ಅದರೊಳಗಡೆ for a particular macrostate, what are the possible microstates you can study. I will give you a simple example to understand this thermodynamic probability. For example, consider a system consisting of 3 particles which are represented by the phase points A, B, C in phase space. The particles considered in the system are A, B, and C. 3 particles are there in the system. Let there are only 2 phase cells I and J for the occupation of these phase points. These particles A, B, and C can be observed either in cell I or cell J. Only 2 cells are there. Let Ni and Nj denotes the number of phase points in ith and jth phase cell respectively. Ni represent number of particles in ith cell, Nj represent number of particles in jth cell. Let us look at the different possibilities now. different probabilities you will observe. Just look at this table. This table gives you the total 8 different possibilities. You observe one by one. First possibility is all 3 particles are in ith cell, no particle in the jth cell. What are the different possibilities? So possible microstate is only one. So all particles are in ith cell means all ABC are in ith cell. There are no particles in jth cell. No other combination is possible. So how many microstates are possible? Only one microstate is possible. And we'll look at this last column at the end. Okay. Let us consider the second case. If there are 2 particles in ith cell, 1 particle in the jth cell, what are the different possibilities? There are 3 possibilities. AB in ith cell, C is in the jth cell. Second possibility is A and C are in the ith cell, jth cell alli B particle irthude. Then B and C are in ith cell and A is the jth cell. That is the third possibility. So in all 3 possibilities, we will have 2 particles in ith cell, 1 particle is in the jth cell. This is the macrostate. It gives only the number of particles in the cell, but microstate gives you the complete information, which particle is present in which particular cell. So total number of microstates possible is 3. 3 different combinations are possible for this 2-1 macrostate. Next possibility, let us take in ith cell 1 particle is there, in the jth state 2 particles are there. Again 3 possibilities. So A in ith cell, B and C are in jth cell. B is in the ith cell, A and C are in the jth cell. C is in the ith cell, A and B are in the jth cell. 3 possibilities are there. So this is called as microstates. So therefore there are 3 microstates which are possible. Last combination is 0 and 3. In the ith cell there are 0 particles. In the jth cell all the 3 particles are present. So only one possibility is all ABC are in jth cell and no particles are in ith cell. So only one microstate is possible. Now look at the total number of microstates possible. Okay, 3 particles ಅನ್ನು 2 cell ಅಲ್ಲಿ occupy ಮಾಡಬೇಕಂದ್ರೆ totally there are 1 plus 3 plus 3 plus 1. Total 8 microstates are possible. 8 different combinations are possible. What are the number of macrostates? 4 macrostates are possible. 3, 0, 2, 1, 1, 2 and 0, 3. 4 macrostates are possible. 8 microstates are possible. So what is the probability of macrostate? 3, 0 iruvanta probability ಏನಿದೆ, that is number of microstates divided by total number of microstates of the system. So definitely it is 1 by 8. Total 8 microstates are possible. Out of 8, this combination is having 1 microstate. So 1 by 8 is the probability of observing 3, 0 particle. 3 particle in ith cell, 0 particle in the jth cell. Consider this macrostate 2, 1 iruvanta probability ಏನಿರ್ತದೆ. So 3 microstates are possible out of 8 microstate. So 3 by 8 is the thermodynamic probability of 2, 1 particle. Then 3 by 8 combination, that is probability is observed for 1, 2 and 0, 3 possibility is 1 by 8. Probability is 1 by 8. If you add them, if you add the probability of each macrostate, you will get the value equal to 1. 1 by 8 plus 3 by 8 plus 3 by 8 plus 1 by 8. You will get total 8 by 8 equal to 1. This is how you can find out the probability of different combinations. You can do one exercise. You consider 4 particles and 3 cells. Let us take A, B, C, D are the 4 particles and 3 cells. Let us take I, J, K. You find out what are the different microstates that are possible for the system. You can put any number of particles in any cell. Okay, there is no restriction on number of particles. Okay, now you find out what are the thermodynamic probabilities for different macrostate. How many number of macrostates are possible? How many number of microstates are possible. Okay, you take it as an exercise, you do it yourself. And I have shared the notes corresponding to this microstate, macrostate, thermodynamic probability, etc. You just go through the notes. If you have any doubts, you can ask me in the end of the session. Okay, we'll move further. So this is about the probability, and analysis of this table gives you, it is clear that the system can be observed in 4 different macrostates and has different possible microstates for each of them. So total of 8 microstates are possible corresponding to 4 macrostate. So just I will show the table once again. These are the macrostates. 1, 2, 3, 4 macrostates are possible. There are total 8 microstates are possible. Note the difference between a macrostate and microstate. Okay, so that is how you can understand. So all the microstates are equally probable and they occur equally frequently. So all possible microstates are equally probable. Okay, but the macrostates 2, 1 and 1, 2 are more probable among the 4 macrostates, because these 2 macrostates have 3/8 probability. That is more probable compared to other 2. And macroscopic properties of the system are due to these macrostates. Right? These macrostates are having more probability compared to other 2. That's why the macroscopic properties are influenced by this most probable macrostates. Remember, the equal probability is applicable for microstates. Macrostate can have different probabilities. Remember this particular point. Okay, so this is about the probability. And finally, we'll discuss this distribution function. What is the meaning of distribution function? We'll try to complete today. So we know that the phase points can be distributed in different ways within the available phase cells of the phase space. Okay, so for example, if you take the example of electron distribution in an atom, so electrons are distributed by means of some condition. There is a Fermi-Dirac distribution function. There is a Pauli's exclusion principle. So there are different laws governing the occupation of electrons in different shells. Bare shell alli ಎಷ್ಟು electron ಇರಬೇಕು ಅನ್ನೋದಕ್ಕೆ ಒಂದು law ಇದೆ. There is a condition. So then we call that law as a distribution function. So that explains how particles of the systems are distributed. Okay, that is called as distribution function. We know that phase points are nothing but particles. They can be distributed in different ways within the available space. Just you have taken an example, A, B, C, 3 particles, 2 cells anta tagondenu. Adaralli 8 different ways are there for distributing that particle. Okay, so that is one example. In general, the number of states are very large and there will be continuous change in their number in passing from one region of the phase space to the other. The microstates can change with time. When system of particles which are in motion, the dynamic system tagondre, the microstates are going to change, whereas the macrostates may be same. Okay, that is how the dynamic system can change their microstate. The number of particles in a given state may change. This can be described by the statistical function called distribution function. So basically, distribution function is defined as the condition described by a function according to which the phase points of the ensemble are distributed in the phase space is called as distribution function. So how does the particles of the systems are distributed? That condition can be described by a function called distribution function. Basically, distribution function describes the distribution of particles in the system. Okay, ಅದಕ್ಕೆ ನಾವು distribution function ಅಂತ ಹೇಳಿ ಕರಿತೀವಿ. Mainly there are 3 different distribution functions that we are going to study in this semester, namely Maxwell-Boltzmann distribution function, Fermi-Dirac distribution function, and Bose-Einstein distribution function. More distribution function now study ಮಾಡ್ತೀವಿ distribution in this particular semester in the statistical mechanics. So first we will try to understand this distribution function properly. Okay, then proper again understand ಮಾಡ್ಕೊಳ್ಳೋಣ. So in phase space, what do you mean by phase space? Phase space is a coordinate system having position and momentum coordinate. The distribution functions are functions of position and momentum coordinates. Okay, a general distribution function in a 6-dimensional phase space may be given by a function which is a function of position coordinate xyz and momentum coordinates px py pz. Okay, ಅಂದ್ರೆ ನಿಮಗೆ ಫೇಸ್ ಸ್ಪೇಸ್ ಅಲ್ಲಿ ಡಿಸ್ಟ್ರಿಬ್ಯೂಷನ್ ಫಂಕ್ಷನ್ ಯಾವ ತರ ಎಕ್ಸ್ಪ್ರೆಸ್ ಮಾಡ್ತಾರೆ? That distribution function must be a function of position and momentum, that's all. If you take the 3-dimensional space Cartesian coordinate system, there are 3 position coordinates and 3 momentum coordinates. Okay, andre phase space ತಗೋಬೇಕು. phase space ಅಂದ್ರೆ ಏನು? It is having position coordinate and momentum coordinate. Okay, so you know that to specify the state of the system we need 2f number of coordinates, out of which f number of position coordinates are needed, f number of momentum coordinates are needed. So this is the system of a system having 3 degrees of freedom. Andre 3 position coordinate beku, 3 momentum coordinates beku. A function which describes the distribution of that particle is defined as f equal to f of xyz comma px py pz. Andre it is a function of 6 different coordinates. Okay, if you want to know what are the number of particles present in between the coordinates x and x plus dx, y and y plus dy, and z and d plus zz, similarly the components of momenta between px and py, px plus dpx, py and py plus dpy, and pz and pz and dpz are given by dn is equal to the distribution function into volume of the smallest element. Basically this dx, dy, dz into dpx, dpy, dpz gives you a volume of one cell in the phase space. That is the smallest volume. And then you phase space and a large number of elements are divide ಮಾಡಬೇಕು. If you divide the phase space into large number of elements, then each element is having the volume equal to dx, dy, dz into dpx into dpy into dpz. So this product is nothing but dv, which is the smallest volume of phase cell in the phase space. ಈ ಸ್ಮಾಲ್ ವಾಲ್ಯೂಮ್ ಅಲ್ಲಿ ಎಷ್ಟು ಪಾರ್ಟಿಕಲ್ ಇದೆ ಅನ್ನೋದನ್ನ ಈ ಡಿಸ್ಟ್ರಿಬ್ಯೂಷನ್ ಫಂಕ್ಷನ್ ಕೊಡ್ತದೆ. ಬೇಸಿಕಲಿ dn gives you number of particles in a smallest volume of the phase space. That is given by the distribution function into volume of the phase cell. That is the advantage of distribution function. Okay, so this distribution function may be Maxwell-Boltzmann distribution function, it may be Fermi-Dirac, or it may be Bose-Einstein. So this is the basic formula to find the number of particles in a phase cell. Okay, so the distribution function explains the distribution of phase points in the phase cells of the phase space. How does particles are distributed? That can be explained using distribution function. Hence, it represents the probability of occupation of number of phase points or particles within the volume of phase cell. Therefore, distribution function can also be considered as the probability density. If you go to the quantum mechanics, you can understand this particular statement. So Fermi-Dirac distribution function is nothing but the probability of occupation of the particle in a given system. So this is nothing but probability density. If you study the quantum mechanics, you will come to understand what do you mean by probability density. So this last statement corresponds to the quantum statistical distribution function. Okay, so distribution function not only gives the distribution of phase point, but also it gives the probability of occupation of the particles of the system in a given state. Okay, you remember this particular statement. Then the distribution function can also be represented in terms of energy. ಈಗ ಮೇಲ್ಗಡೆ ನಾ ಏನು ಹೇಳಿದೆ, distribution function is represented in terms of position and momentum coordinate. You know that the momentum gives the kinetic energy for the particle and position of the particle gives the potential energy for the particle. So you can express this momentum coordinate into kinetic energy. You can express this position coordinate into potential energy. You know that kinetic energy is given as p square by 2m, momentum square divided by 2m anta baribodu. Position, how to express the potential energy? It is given by mg into h, where h is giving you the position from the reference level. Okay, that's why momentum coordinate can be expressed as kinetic energy coordinate. Position coordinate can be expressed as potential energy coordinate. So finally, you can express the distribution function as f of e, where f of e is the distribution function as a function of energy, that's all, into the density of states or number of states having the energy E. If you do this product multiplication, you will get the total number of particles present with energy E. Energy E ಇರುವಂತ ಪಾರ್ಟಿಕಲ್ ಎಷ್ಟಿದೆ ಅನ್ನೋದನ್ನು ಫೈಂಡ್ ಔಟ್ ಮಾಡಲಿಕ್ಕೆ ಏನು ಮಾಡಬೇಕು, you take f of e into g of e, where f of e is the distribution function as a function of energy, g of e is the number of available states having energy E. Okay, so that gives you total number of particles having the energy E. That is how you can understand. Okay, so you just remember, distribution function can be expressed as function of position and momentum coordinate. Also, you can express the distribution function as a function of energy. That's all. Okay, so that you can remember. So if you want to know what are the number of particles present in a small cell of energy dE, then you can do this particular equation. So just you multiply dE on both sides, you can get the number of particles present in this volume dE. So here dE gives the volume of the smallest element in the energy space. You remember this particular point. Okay, that is how you can find out number of particles present in small range of energy dE. Okay, so that is about the distribution function. So we will stop here.